CIT 1123 presentation video, module 2, submodule 4, modifying single area OSPF. Let's get a couple of looks at this. First thing they want to talk about is how the OSPF calculates the cost. So if you have two neighbors and each neighbor has a path to network X, you'd want to know which path you should take. So you calculate your cost to your neighbor plus whatever your neighbor reports back to you equals your cost to that destination. Whichever cost is lower goes into the routing table. The other one sits in the topology table and waits to see if your primary path becomes unavailable. If it does, then it will kick up into the routing table. I think that's the easiest way to identify that. Now, the thing about OSPF is it was created a long time ago when 100 megabits per second was a really fast connection for a WAN style connection. And it still is, but we can go faster than that now. So 100 megabits per second, 1,000 megabits per second, 10,000 megabits per second. These are all speeds that we can go at across long, wide distances. So what happens is the cost value, which is the cost of the reference bandwidth divided by the actual bandwidth, will give you the cost value. So if the reference bandwidth, which is 100 million, is divided by something like 10 billion, it gives you a cost of 0.01, which equals a cost of 1. So we round up to the last whole number no matter what. When we have gig Ethernet, we have 100 million divided by 1 billion equals 1. And 100 million divided by 100 million equals 1. And 100 million divided by 10 million equals not 1, it equals 10. And those are not the same. Thanks, Cisco. Let's just take that part out of there. So Ethernet, we can distinguish the difference between Ethernet and fast Ethernet, but anything beyond fast Ethernet, with the reference cost bandwidth being 100 million, we can't distinguish among those speeds. So what we have to do in today's day and age, if you're going to have a link that's faster than 100 megabits per second, is you got to change that reference bandwidth value. And the way to do that is use the command auto cost reference bandwidth, and then you put in the value for megabits per second. So if you have something that's as fast as 1,000 megabits per second, you would use auto cost reference bandwidth 1,000. If you have 10 gig speeds, then you would use auto cost reference bandwidth 10,000, and then at that point, at 1,000 gig speed is a metric value of 1, and 100 megabits per second is 10. And 10 megabits per second is 100, and you get the idea. The cost goes down from there. So that's the long and the short of that. This slide just shows how that could be added up. So if you see the speeds of these links and how we accumulate cost, if we're on, say, router 1, and router 1 wants to get to network 10.10.2.0, remember that network because it's going to be important all the way through this section. So we want to go from router 1 over to 10.10.2.0, and we want to calculate the cost. Well, there's two paths router 1 can take to get there, right? So there's this path, and then there's this path right here, right? So router 1 is going to put out its hellos, and it's going to form neighbor relationships with router 2 and with router 3. Router 2 is going to advertise that its path to 10.10.2.0 is a cost of 1 because it's a directly connected interface. So R1 is going to remember that my path through R2 with my cost of 10 to get to R2 plus their cost of 1 is going to be, the path through R2 is going to equal 11. Now, if we go the other way, R1 is going to learn that R3 has a path to 10.10.2.0, and its path costs 10 plus 1 is 11. So R3 is going to report 11 plus the 10 that we already know about, and that's going to be 21. And therefore, that will just go into the topology table, and the path through R2 will be the path that we'll use because the metric is lower, and that will go into our routing table at that point. Okay, so that's how you can look at that. So this is just calculating the whole. This is just showing you exactly what I just said, and we're good to go at that point. If we look at our routing table now, because we know that's our best path to router to 10.10.2.0, here it is, show IP route, and they've used a pipe to show only the one network. So 10.10.2.0/24, and then we see a value here. We see administrative distance followed by the metric value. So we just calculated out that it would be 11, and we can see the metric value is 11. The administrative distance value of 110 is the default administrative distance value associated with OSPF within the Cisco operating systems. So we know if we look at this and then we look at this, we're going to know that those are together. So the O for OSPF means the default administrative distance is 110. The metric value for this is 11, and if we were to look at the topology table, there would be another entry that would have a value of 21. 21? 21. 21 for going through router 3 as opposed to going through router 2. Okay? So keep that in mind. Now, in this case, they're just showing you the auto cost reference, IP cost. Oh, so say you wanted to change the value of that particular interface from 1 to something different, you could do that, and that's all they're showing you here. Just in case. See, the thing about routing in general, and this is just an overall thing, is what you learn in CCNA is how to put the systems together, how to build routers and switches so that they do what they're supposed to do natively. And then when you get into the CCNP courses, you learn how to lie to your routers to make them do what you actually want them to do, not just to connect, but to be more efficient at that. So at this point, though, for CCNA and really, kind of the beginning of this course, this is a command you're probably not going to use very often, but it's essentially you're just going to go, you know what, this isn't working the way I'd like to, and I know it's set up correctly. I'm just going to fudge it a little bit, and I'm going to change the cost of that path to 30 as opposed to 10, right? So that's what they're getting into on that slide. Let's move on to the next slide here, and you can see the cost value has now gone up to 50 here. As it goes through the other path. So this is just testing the failover. They've actually made some interesting changes here. It would be cool if we could have followed this along, and then this particular entry here to 10.10.2.0, which we've been talking about, would have a metric value of, say, 21, which is what it would have been if we would have gone through R3. But then they went in and they jacked around with the cost value of the loopback interface on router 2 and changed it to 30. So now it's 30 plus 10 plus 10, which gets us to 50. We can still get there, but they kind of just do a little roundabout in order to get to that place. So that's that. Hopefully this is making sense. We'll move on to the next couple of slides. Show IP OSPF neighbor, really cool command. Shows the hello and the dead time. When we talk about hello and dead times, a couple things. Number one, your hello and dead times need to match between your routers so that they can become neighbors. The default dead time is 4 times the hello. So if the hello is 10, then the dead is 40. So what does that mean? It means that when a router gets a hello from a neighbor, it says, oh, hey, I have a neighbor, and it takes that neighbor's router ID, and it puts it into its neighbor table, and it respects what that neighbor has to say, and it listens to the database descriptors and the updates from that neighbor, and it uses them as information in its very own OSPF database. So in this case, neighbor 3.3.3.3 has sent an update to, or a hello message to router 1, because that's where we are right now, and the dead timer is going to start counting down. Now, the dead timer is going to count down from 40 because what happens is in 10 seconds, when this reaches 30, it should receive another hello from neighbor 3.3.3.3. Now, if it doesn't, it's no big deal. It stays in the neighbor table, and we still respect and believe what our neighbor 3.3.3.3 is excuse me, telling us. So we're going to give 3.3.3.3 a little bit of leeway that if it doesn't send us its hellos every time it's supposed to, we're going to say that if it misses 4 hellos in a row, we're going to stop paying attention to it, and we're going to go ahead and take it out of our neighbor table, and everything that we learned from neighbor 3.3.3.3 is going to get purged from our system, and then we're going to tell all of our other neighbors that everything we had learned, all those changes that we just made, we need to let them know those things. So the hello timer, usually set at 10, the dead timer, 4 times the hello, which is 40 seconds. That's the way a router can keep track of its other neighbors. If you want to change those because you want the systems to update faster, you can change them. But remember, if you change it on one, you should change it on all of them because you want these to match. Otherwise, you're going to end up in situations where you might have one device is thinking it's supposed to get a hello, and the other device is thinking, I don't really care when I send it, and you can set the hello back, several seconds. You could get into a situation where you start having what's called a flapping situation, where a router will be declared dead by a neighbor, and then right after that send a hello, and it'll kick back on, and then it's got to, it's going to create a lot of extra processing. So my advice to you on changing hello and dead intervals is don't do it. If you have to do it, make sure you do it on every single device, and you're in step with all the other people you work with. Okay. All right, so that's cool. And here's the change of those hello and deads. Great. We can get through 5 as well, 2.5. Default route propagation. Here's the thing. I might have a static default route that's set up to set me out to the internet, right? So what I would want to do is if I have a default route to the internet, I would be able to send all of the information that does not match any other routes in my system out to the internet, and that's probably where it goes. All the other routers that are within your system will also want to have that static default route. So rather than building a static default route and having it, kind of know how to get from where it's at to the internet, what we could do is we could advertise it within OSPF. And the way we're going to do that is we're going to use the command default information originate. Now, I think if you think back in RIP, I think that when we learned RIP, we used the command, we might have used default information originate in RIP, but we might have used redistribute static. So there are a couple different ways to get that done. In OSPF, the command is default information originate, and it just means redistribute. If you have a static default route, thus the command default information, if you have a static default route, inject it into the OSPF system and tell your neighbors that you have a path out to the internet is essentially what you're doing. So this particular router here has a interface loopback 1, and we're going to use that as our internet value, and we're going to use the command IP route quad zeros loopback 1. So the loopback 1 interface would simulate your last hop before you would head out to your internet service provider. Within OSPF, we're going to add the command default information originate, and then all of our neighbors will learn about this static default route that we've created. The best part of this is if your primary path to get to router 2, which is now the router that's connected to the internet, it fails, you can relearn that static default route through a secondary path, and you wouldn't want to hard code that static route in there. More on that when we do the labs. There's a really nice lab on this. It really works out pretty good. And this is just showing here router 2. It has a static default route that was created with that IP route command. This is going to move something, and I don't want it to. And then if we look at router 1, it's redistributed the static default route, and it's not an S in router 1. It's an OE2, which means an external 2. Just means that someone used a special command to get this path into the routing table of router 1. More on that later also. But you can see it's the same path, and it's going to find its way to router 2. Router 2 is going to send it out to the internet, and that's how that is going to work.